Okay, so hello everyone. So today, obviously, you did not have. Oh, can you guys mute, please? Um, no, I'm muted on Discord for sure. Um, but yeah, not on Twitch now. Okay, so yeah, you guys did not have a daily for today. Okay, that is weird. Um, right. So basically, we're just going to keep going through the subspace topology, and we'll probably introduce ourselves to the product topology. So, I don't know if you guys read through it at all. I'm not really assuming that, because I know you guys are working on the take-home exam. So obviously, feel free to stop me. I'll try to draw some pictures here, and we can discuss as needed. But yeah, we can kind of try to keep it interactive, but obviously I know that you guys are a little less prepared than normal. Okay, so let's remind ourselves, whatever works best for your learning. Obviously, like I will be exporting these, but do you mean daily or like problem set? Well, not daily. I'm not going to have you go back through something. Yeah, this will be most likely your exposure to them. Yeah. Right. So we have a subset of X, right? We have some topology on X, and then we say U or V is open in A if V is U intersect A, where U is open in X. Right, and so, I mean, these are open sets. We would like to still have closed sets, right? And so theorem 147 is exactly about kind of a nicer condition, right? You would kind of hope question mark is, C closed in A if C is equal to, F intersect A, where F is closed in X. Because that's not the only way we define closed, right? This would be like if you use the closed definition for topology instead of open sets as your definition for a topology, then this would kind of be the natural subspace topology thing. But the way we initially defined closed sets, right, was it's the complement of an open set. And so like our definition for closed is C is closed if its complement inside A, right? Because we're talking about the subspace topology on A, so that's kind of our universal space in that case. So if A minus C is open in A, right? And so, of course, the in A part is important there. And so our goal here is to show that these two things coincide, okay? That A minus C being open really means that you could have just said C was some intersection with a closed set in X with A. And so that is 147. So this is, a subset of X. X has some topology T. And then we want C is closed in A using this definition, if and only if C is equal to F intersect A, where F is closed in X. So this is our goal. And I think it may help to look at a picture here, just to kind of see what's going on, right? So we can just draw X here, and then, you know, who knows what A looks like, right? Maybe it's like a half open kind of thing. So I'll draw some dotted, some not dotted. This is my A. And then what we're kind of trying to say here, right, is, all right, if we have a closed set here, this is F, you know, I've closed my boundary off, then C, the intersection would be this guy. And so the thing in red is C, and then the question is that closed? The question, right, is A minus C open? So A minus C is the stuff over here. And so is this open? Who knows? So does that picture make some sense? It's kind of what we're looking at. And right, like the whole issue here is the same stuff that we saw last time when we talked about, like, you can add boundary points, right? Like we had A be the closed interval from 0 to 1, and basically, you know, adding that endpoint 0 or the endpoint 1 would make something not open in R, but it could be open in A because you can intersect an open interval and it like cuts it off there. And so the idea is that closed sets, you know, you would hope, right, that like 1/2 to 1 would be closed in A, because, you know, having a closed interval in X is closed. And so, you know, this is the hope that that coincides. And we see here that, again, like weird stuff can happen along the boundary when you intersect with A. Like we can have a closed set with some open stuff here. You know, if I had, for instance, if this was A and I wanted to consider 1/2 1 intersect A, right? Then I suddenly open a side, but if this theorem is true, then this would be closed. So again, weird stuff can happen at endpoints, basically, is the point. So let's try to prove this. Okay, so let's go this direction. Okay, so here I have the definition, right? I know C is closed in A. So this just means that A minus C is open in A. So if A minus C is open, well, we know that A minus C being open in A is just the intersection of some open set in X with A, right? So it's U intersect A, where U, I'll just say, is in the topology on X. All right. So then we want to figure out, is C, F intersect A, where F is closed in X. So what is the only thing that really comes to mind as a closed set in X from this situation? Do you guys have any idea? Is that a no? Yeah, so given this situation, right, where we know like A minus C is open in A, U is some open set in X, like is there any closed set that naturally comes to mind in X that would be our candidate to intersect with A? Yeah, exactly. So our guess is F is U complement. That'll be for the other direction. F complement would be. I mean, it's like a, I don't know if it's completely trivial, but I agree it's not super hard. Okay, I'll let you prove it then. Okay, so basically my goal here is I want to introduce U complement, so I'm just going to like complement both sides, right? So like A minus C is this, right? And so what is C? C is the rest of the stuff in A that's not in U intersect A, right? That's just, yeah, A minus C, I basically just flipped those. I took the complement inside A of each of these. And so what do we get from this? Well, we know what the set minus means, right? I'm now intersecting U complement union A complement using De Morgan's laws. And if you want, we can split this, or you can just kind of see what's going to happen anyway. I mean, what is A intersect A complement? This is empty, right? And so really, we've boiled it down. Yeah, those are equivalent. Right, because that's what I have done, right? Because this is empty, I mean, now we have that it's A intersect U complement, which is exactly A minus U. But this is our F, right? Because we know that this guy is closed. And so we get that direction. We now have C written as A intersects some closed set in X. And basically that was just coming from like recognizing the candidate to be our F is going to be U complement. So the other direction, maybe I'll just set it up. So let C be F intersect A, where again F is closed in X. Then how do we get A minus C to be open? Yeah. Kinda, yeah. So I think I would want to go through the same thing, but yeah, I mean that's basically it, right? So what you're saying is this, right? Like take away the rest of A. Right, yeah, and I mean that is what you said, right? This is just put into symbols, and then you could do the same thing as above, and basically this is exactly A intersect F complement, and that's exactly what you're saying, and so we get A is open, or sorry, geez, so A minus C is open, so C is closed. Cool. All right. Okay, and so, by the way, just hit me up if you have questions. Just type like question mark in a chat or something like that, and let me know, or just hop on the mic. So the next one is basically showing that closure is transitive. Okay, so if we have this string, right, where C is closed in A, and A is closed in X, then C is closed in X. Which kind of makes sense, right? I mean, we've like intersected a closed set with another closed set. It's going to be a closed set. That's basically what this boils down to. Hey, abelian topology. And that is basically the proof, right? We know closed sets are remain closed under intersections, even arbitrary ones, and so that basically just uses 147, right? We want to use that definition, and that's kind of why we have it. It's easier in this case to think of it as being an intersection with a closed set, because in this case that allows us to view it as an intersection of two closed sets. So, right, C being closed means C is F intersect A, where F is closed in X. Sorry, I should be clear every time where it's closed. And F is closed in X. All right, and then we know A is closed in X. So F intersect A is closed in X because it's the intersection of two closed sets. So that one is super fast. Okay. Alrighty. Okay, so Hausdorff. So we're going to see this as something, we'll have a similar result for the product topology as well. But basically Hausdorff is a nice property. We've already kind of seen that a little bit, right? That, you know, open sets, closed sets, separating points, like this seems so much easier in the standard topology on the real line as opposed to, say, the countable complement topology, which we showed was not Hausdorff last time. And so this ability to separate points, basically distinguish yourself from your neighbors in some way, is useful. And it's also something that makes sense, right? That when you pass to the subspace topology and you suddenly look at like a subset, but you're using the same kind of open sets, that you should remain Hausdorff, right? You should still be able to separate things that were inside something in which you could separate them in. So it turns out that's true. So basically, subspace topology, Hausdorff property remains. So statement, so let X be Hausdorff, and A be a subset of X, then the subspace topology on A is also Hausdorff. All right. So again, like weird stuff can happen at endpoints, but that's about it, right? And point is, if we can separate them initially, we should be good. So take a couple of points in A. All right, let A and B, say B and A, with A not equal to B. Well, it's still inside X, right? So since A and B are in X, we know there exists open sets that are going to separate them. And so there exists some, say, U, I don't even need to label these, U and V open in X, such that A is in U, B is in V, and these guys are disjoint. And then the idea, right, is we can separate them there. We just intersect these guys with A, and that's exactly how we get our open sets, right? So then A is in U intersect A, B is in V intersect A, and if they were initially disjoint, then intersecting with A isn't going to suddenly give you something, right? So U intersect, U intersect A intersects V intersect A is also the empty set. And this is a good one also to maybe like have a picture again, right? So you've got like A here, and this is our U, B over here, with V, and then maybe A is something like this. And the point is like, okay, sure, we cut off some stuff, but like they're still separated, right? I really like the purple. Okay, so now we need to talk about, right, we've talked about, oh yeah, respect. So we've talked about open and closed sets, right? And so like what followed that before when we weren't talking about the subspace topology? Well, we talked about like the smallest closed set containing something or the biggest open set contained in something, like the interior and the closure, right? And so it's useful to have these notions still, but of course we're not talking about the closure in X. Now we need to be specific and say like the closure of a subset of A inside A, right? Or the interior of some subset of A inside A, where you're not considering open sets in X that are leading up to it, but rather open sets in A leading up to it. So we need to improve our notation in order to distinguish these things, right? So if I want closure or interior, right? So let's take a subset here. So we're really focusing on the Y guy here. Then if I write the closure of Y or just Y bar, that's really like inside X, right? And so what I'm going to do is just drop a little subscript in here, closure of Y inside X. All right, so this is closure of Y in X. And then if you want to think of it only in A, right, this is the closure of Y in A. And it's going to be defined the same way, right? So the closure of Y in A is the intersection of all closed sets in A containing Y. Right, so the same definition, but just restricting yourself to closed sets in A. And similarly, right, and this is where like this is where the CL is better than the bar because you can specify, right? And so you want the same thing, right? So the interior of Y in A is going to be the union of all opens in A contained in Y. All right, so that should make sense. So a natural question that might come to you is there some relation between these, right? So we said that closed sets in general, right? So, C is closed in A if C, is equal to A intersect F, right? Where F